Hi, I'm going to show you how to calculate pressure in a static fluid, and I'm going to show you how to use the definition of pressure to calculate a force. So the definition of pressure is this. We use a symbol P for pressure, and it is force divided by area by definition. But most of the time, we don't use the definition of pressure to find pressure. We actually often use this definition to find force. So we have force is pressure times area. Okay, so how do you find pressure? Well, it depends on the physical situation. If it's a dynamic fluid, that's a different situation. But if it's a static fluid and we have a reference point where we happen to know the pressure, then it's a fairly straightforward method to calculate the pressure somewhere else. So you have to know the pressure somewhere. Okay, and I'll use the symbol P naught for the location, the pressure at the location where we happen to know the pressure. Often that's atmospheric. We have something bent into the atmosphere, and we know the pressure somewhere, and so we can calculate the pressure anywhere within the static fluid using this formula. So this is pressure somewhere. This is pressure where that we happen to know. This is density of the fluid. This is G, 9.8 meters per second squared on Earth, and then D is depth, so distance below the reference point. Okay, again, usually that's the surface and it's atmospheric, but it doesn't have to be. Okay? So let me give you a scenario. Let's say we have a submarine at a depth of 50 meters below the surface. And now we're going to find the pressure. Okay, so water is pushing on all its sides. Of course, the pressure below is a little bit greater than the pressure above, but just because they're at slightly different depths. So let's just call the whole submarine it's all at about 50 meters, and let's calculate the pressure for that submarine. So we know, and we'll use. I'm going to be lazy here, and I'm going to use the density of regular water, but of course most submarines are in salt water, which has a slightly different density. But anyway, so we're submarine at a depth of 50 meters, so in water. So we know that the pressure at the surface is 1.013 times 10 to the fifth, and I know that the density of water 1,000 kilograms per cubic meter. Of course, we use 1,030 if it was in salt water, so we're going to be a slight underestimate of the pressure here. G of 9.8. Of course, we know exactly where this was. We could get a more precise value. And then D is depth. So we don't use negative numbers here. Okay, we're 50 meters below the point where we know that the pressure is 1 atmosphere. And so we use a positive number. So I think this is intuitive. Pressure goes up with depth. So we can calculate the pressure, throw those numbers in our calculator, and find that at 50 meters below the surface, at least in pure water, would be 5.91 times 10 to the fifth pascals. Okay. So that's the pressure. Of course, we can compare it to this one. It's almost 6 atmospheres. So for each 10 meters below the surface, rough rule of thumb is that we get an additional atmosphere. Okay, so what practical effect does this have? Well, what if the submarine, we want to put a window in the submarine? Okay, not very common, but I suppose for if we're not going too deep, maybe we can pull this off. So let's say we need some dimensions so that we can calculate the area. But let's say we have a window with we'll use a circular window with a radius of 20 centimeters, or point. I'll go ahead and convert that to meters, 0.20 meters. Okay, a circular window, and so I want to find the force exerted by the outside water on that window. Okay, well, we can, like I said before, typically we use the definition of pressure to find the force. So that's what we'll do here. So force is pressure times area, but instead of area, I'll do some geometry, pi r squared for the area, and then we can just throw in the numbers. Okay, so I know that the pressure is 5.91 times 10 to the fifth times pi times the radius, 0.2 squared. I throw that into my calculator, and I get an answer of 7.4 times 10 to the fourth newtons. Okay, so what can you compare that to? Well, that's about the weight of 7.5 tons. So, 7.5 metric tons. And so that's not a big window, okay, 40 centimeter diameter, and it has an inward force of 7.4 times 10 to the fourth newtons. That's a lot, okay. It's as if we had 7.5 tons sitting on top of it. There is, of course, an outward force from the air inside on the other side of the window. So presumably, roughly atmospheric pressure multiplied by this. But so we'd have to subtract that off if we wanted to get the net force of the, comparing the force of the outside water to the inside air. But still, there's a lot of force on that window. So anyway, that's it for now. So just remember that the definition of pressure is usually not the way we find pressure. For pressure in a static fluid, you usually use this formula, and then you can use the pressure to calculate a force if you need to. Okay? All right, thanks for watching. I'll see you next time.